Good afternoon. Good to have everybody here today. What we're doing starting today is getting into a category of parametric equation problems called, it's a real world situation problem. I call these parametric equation sports problems. And there are different situations than sports, but these tend to be pretty common problems, pretty common representations. If you think of it another way, you could think of it as a rocket or a ballistic or something. It could be anything, but here we're given two equations. Kevin hits a baseball at 3 feet above the ground with an initial speed 150 feet per second at an angle of 18 degrees with the horizontal. And the question, will the ball clear a 20-foot wall that is 400 feet away? Now, what my goal is for us in this class over the next couple days is to be able to take this thing here, the text, and for this text, they're giving us the parametric equations. I'd like for all of you to be able to learn to take this text to be able to create these equations in the situations. And so we're going to, so just pay attention for that, because that's a goal here. And so here's the parametric equation. So we're going to enter these in our calculator. And a lot of this has to do with setting the window right. So here we are back to our calculator. And one thing we need to concern ourselves with is that the parametric equations we deal with are in degrees. So accordingly, we need to make sure our calculator is set to degrees. So our calculator is set to degrees. That's going to help us. Pardon me? So now we go to here. Okay, we're not in parametric mode. So what I'm going to do is go to this mode here and change this to parametric. And then we have our equations here. And it's going to be, I think, is it x value is 150. Is that right? Cosine 18 degrees, and we know we're in degrees because of this up here, right? And then t. All right, so that's going to be, this is going to explain the horizontal motion of the baseball. All right. Now let's go here, and what we're going to have is there's more complication, more detail needed on the y usually. The part is where the ball starts vertically, and the ball leaves us at 3 feet off the ground. You, instead of go with this horizontal motion, you're going to have a vertical motion, which is going to be 150 what? Sine 18 degrees times t. And when it comes to the effect of gravity on this planet, we're going to have negative 16 t squared. And gravity does vary a little bit throughout the Earth, depending on elevation and other factors, but it's really within a very narrow tolerance for where human beings and animal, plant life exists. So, pardon me?
We talked about that in physics.
Oh, you did? Okay, very, very good. And so there are other things involved here, like in baseball, there's air resistance. So this is not perfect, but for the purposes of this class, this is where we're going to have it. I'm going to come up here and turn my plot 1 off, And when I graph, I get this, and this is a standard window. Now, we don't see, what you're looking for is the ball to be going up, which definitely it looks like it is from 3 feet. But you're looking for the ball to descend down, and I want to go look at the problem again to make the right adjustment to the window. So we go over here, and we see a wall that's 400 feet away, so that's going to help us figure out what's going on. So we come back here and go to window, and we have T max of 2 pi, and so that's 6 seconds. That's going to be long enough for a 400-foot baseball to go, right? So we can leave that alone. I'm going to change this T step to 0.05, as we've been doing for the other problems. You remember that? And you can even change this for even better resolution than that, perhaps. X minimum is fine, but X maximum, we need to have that wall 400 feet away. So I'm going to make our wall, I'm going to put this wall at 420 is where I'm going to put it. And then as far as Y scale, I want to see the top of the hit. So you can put like 100 feet here, something like that. You can really adjust that if needed. So now you're going to graph this and see what's happening, and then you see something like this. Does that look right?
Yeah.
Does everybody understand you don't see that here?
I
didn't get that.
Here, let's go ahead and let's help you. I'll help you listen. So what you have here is that, scale. Okay, Y max, okay, 100. So maybe you do that. There you go. Yeah, the Y max wasn't set up, okay? Is everybody good on this now? Who's helping you get set up? Yeah, Elizabeth's Y max was a little bit, wasn't set up right. Okay. So, let me just wait just a minute. Did you figure out where it was not set up right? Did it help you in physics to be comfortable with the formula? No, not?
It's because that's where I got everything. Probably affected if she remembers.
But the negative 16t squared, remember that from physics? Should remember that. And the thing you have for meters, it's negative 4.9 squared, t squared, for meters. So those are just some numbers to remember. Let me see what we're looking for next.
You were in radians.
It was radians? Yeah, radians can mess you up. So this is asking a question, and really it's a leading question. Approximately how many seconds after the ball is hit does it hit the wall? So you got a 20-foot wall, and so it answers the question I would ask before this question is, does the ball go over the wall or not? Well, according to the way this question is framed, the ball does hit the wall. So we go up here, and we go to trace. And when you go to trace, you go like this, you can trace the path of the ball.
It's not going to make it.
And one thing I notice is it's going every 0.5 seconds. And I might want to even, so it's 400 feet away. How close to get? So we're real close, right? So this is as close as we can get. I don't know if we go to 0.1, if it makes it 0.01, it makes any significant difference. 0.01, I don't know. And then trace that. Because sometimes, now the problem with this, when you do 0.01, what's the problem with it? It takes more time, doesn't it? It takes more time to trace all the way over. But you get better resolution. So that's something you can tinker with as needed. So here we're getting close to, we see that we're below the height of the wall, right? And one thing you look for when you do this, you can find your maximum height. You can find the time it takes for the ball to get there in seconds. And here we are, as close as we're going to get. And so we're 2.8 seconds and about how high on the wall? 7 feet. So yeah, between 7, so about 7 feet. So we will say 2.8 seconds, right? So 2.8 seconds. And it says about 7 feet, right? And then Ride to Learn, explain why Kevin's hit might be caught by an outfielder. So why might Kevin's hit be caught by an outfielder, maybe?
Because it hits the wall.
Well, it hits the wall, but how high does it hit the wall?
7 feet.
7 feet, right? So I might be the height of an average outfielder, right? And so reaching above, a little over 6 feet tall, I can reach up 7 feet, right? So I could catch that, couldn't I?
Yeah, you can totally do it.
Catch it with a hat, maybe. I catch it with a glove, couldn't I? I wouldn't have to jump or do any kind of weird gymnastics. I could just reach up and catch it. So that's why an outfielder could probably reach above his head and catch it, right? So the outfielder, abbreviated outfielder, can reach up and catch the ball. At that height. And explain why his hit would likely not be caught by an outfielder if the ball had been hit at a 20-degree angle with horizontal. So what we're doing is we're talking about a sensitivity analysis, aren't we? Sensitivity analysis has to do with changing one aspect of it. So we can change this, can't we, to 20, right? Oops. See what happens at 20. Same thing, we just had to change the numbers, didn't we?
Yeah.
And so you can kind of see the ball lofting higher, can't you? Just the way it looks. And then if you go to trace, we can do what we did before. Now this time we're getting to a maximum height of, still going up, 41, 42, 43, 44. Now it's going down. So it got to a maximum height of about 44. So now we're coming down to 400 again. So we're right about 400. And where does the ball hit the fence? It does, right? Barely. So it's just about over the fence, but not quite. But is that outfield going to catch that ball at 19 and a half feet off the ground?
No.
No. Okay. So ball's over 19 feet. At 20 degrees, no, because ball will hit near the top of 20-foot wall, right? Okay. So that's number 43. Questions on that? I don't know about you, but I sort of like these problems here because I feel like this is, it's kind of applying what we learn in trigonometry and parametric equations. So here we have 44, another situation where I want you to work that out. In this case, they don't give you the equation, right? So I want you to see if you can piece together that equation from looking at problem 43 and kind of see how we do on that. And I'll call on somebody here in a couple minutes. Okay, what I'm going to do is call on somebody to help me get the equation down that we put in here. Fifth period. All right. We get Elizabeth. Okay, Elizabeth, did you come up with an equation for this?
Yeah.
Okay, good. So if you can just tell me what that is, and we'll write it down here and try it out. Go ahead.
Equals 120 cosine 30 degrees t.
Okay.
And then y equals 4 plus 120 sine 30 degrees t minus 16t squared.
Okay. You notice something I did when I wrote her equation down for me, for her? You know what I see what I did?
You,
0.5
0.5.
sine 30, sine 30.
Can I do that? Yeah. So there's some shortcuts. I also could have put square root of 3 over 2 here for that. So this happens to be one of those trigonometric ratios where these are standard unit circle points. So let's go ahead and tell me, did you already put this on a window, Elizabeth?
Yeah.
You did? Okay. So I want you to tell me, let me go ahead and I'll enter it here, 120 cosine 30. And over here was it 4?
Yeah.
Plus 120 sine 30. Oops. Oops. Sine 30 less. So we have that. Did you What about the window? Did you do anything different with the window?
No, I left the window as is.
She left the window as is, so we left this right here like it was. So you just graphed from here? So you can just kind of see compared to the other one was a flatter hit, wasn't it?
Yeah.
Like here, it's higher. So next we come to the questions, right? We have everything looking good. So does the ball clear the fence?
No.
No. So let's go ahead and hit trace to verify. So it's a 350 foot away. So 350 feet away. So right here, at the very apex, we're at 60 feet in height, or a little over 60 feet in height. So we're going to 350. So we're getting close to 350 right here. So that's about as close as we can get. So how high are we on the wall there?
24 and a half.
24 feet. That's a 30-foot fence, right? So no. If so, does the ball clear the fence? Well, no. If not, can the ball be caught? Okay. Ball, would you say ball cannot be caught? And why is that? Because
24 and a half feet.
it's 24.5 feet off the ground, right? Now what I want to do is we're going to use problem 44 and go into problem 45 into our next exercise set after this. We're going to be working on I have another insert exercise set on parametric equation sports problems. So I want to put that in your hand and just have you look at it. And we'll probably go over this some on Thursday. What's happening tomorrow in class? Do you remember? Okay, juniors are having an English test, right? And seniors somewhere have an AP English, right? And I don't know when you guys are going to be done, but so what I want you to do is 3, 2, 1.